Learning target, I can calculate C values of initial value problems, inclusive of differential equations. So, first a little review. Okay, let's consider two equations we have here. Y equals x squared plus 3, and y equals x squared minus 5. So if I were to take the derivative of the first one, it would be what?
2x.
2x. If I was going to take the derivative of the second one,
2x.
it would also be 2x. So, it doesn't really matter what a constant was in the original equation, does it?
No.
No, it does not. Alright? However, let's try the reverse operation. Alright? I need to integrate this. I'm going backwards from the derivative, don't I? The integration, yes, of 2x dx is x squared. But,
Where's the variable?
we don't know what the constant was. It could be 3. Alright? It could be -5. It would be 2x. It could be whatever. Alright? So, this is why we put a plus C in the answer. That reminds us that there might have been a constant. Well, maybe it was 0. I don't know. Well, there was a constant there. That's why I put in the plus C. I know there's been some sort of, questions about that. Well, now you know. Alright? Not too crazy yet. Maybe if we have some more information, we could actually find what C is. So, if we're given the derivative of a function to be 2x, and y equals 4 when x is 1, find the equation for y. Alright? This is called an initial value problem. Because we need some sort of initial values to find that constant. It's like back in the day when we used to create the equation of a line in integrated algebra, and make the slope and a point. Well, you can't find that b value unless you put the slope in front n, and you put that coordinate into the x and y, and you can solve for b. It's the same thing here. Okay? An equation containing a derivative is called a differential equation. That's it. Don't freak out when you hear that term. That just means derivatives. You guys have been working with it. Alright? There's actually a class called differential equations. People like to call it DiffEq. I don't know why. It sounds snappy. Doesn't make it any easier. And it's considered an equivalent of like Calc 4. Right? It becomes an initial value problem when you're given the initial condition and asked to find the original equation. So let's do this. Let us do this. Right? We just figured out that if we integrate 2x, we get x squared plus c. That's my original equation. Okay? Now we can actually find out what that c is when they give us the initial values of the problem. Y is 4 plus our x is 1 equals. And now I get 4 equals 1 plus c, and c is 3. So in my initial problem, y would equal x squared plus 3. It's really not that difficult. They just start to step it up with their derivatives and all that jazz. Okay? So if I were to look back, this is a problem I would use if I was given the initial condition where y is 4 when x equals 1. Alright? Any questions on this so far? No, it seems pretty simple so far, right? So far. I like that phrase. Slope fields. I don't like doing them. I don't really think they ask them that often on the exam. initial value problems and differential equations can be illustrated with the slope field. So, slope fields, as it says right here, are mostly used as learning tools. Okay? They help you get better at things. And they're mostly done on a computer or graphing calculator. But a recent AP test asked students to draw a simple one by hand. And really, slope field is really just, it's an axis. It's a grid where you just draw what the slope would look like in that corner. You don't even have to draw a graph. Just right in that corner, you draw whatever the line to look like what the slope would represent. It's really place. But let me show you something. All right? Let's use our example here. Y prime equals 2x. We're going to use this to death here today. Here's what the slope field of this looks like. Okay? First of all, when we integrated that, what did it give us? It gave us x squared. Isn't that a parabola? Which means, because we don't know the c value, our parabola, I'll draw it here. This is what a parabola looks like. Correct? Fantastic. Now, I don't know what C is. So what if C was our plus 3? Well, then this would move up to 3, wouldn't it? What if our C was minus 2? Well, then that would move down to minus 2, wouldn't it? But no matter where it is, once it gets to the right side, it gets steeper, doesn't it? Once it's across the y-axis, it has a slope of 0, which is horizontal, doesn't it? So it kind of gives us an idea of what the graph's going to look like. And if we have our actual derivative, this is slope, isn't it? Okay, well, I can technically take any coordinate here. How about this one, right here? And at that coordinate, it's what? X is 1, y is 0, right? So x is 1, y is 0. What's my slope? Well, when x is 1, there's no y to put in there, is there? My slope is 2. So guess what? This line is a slope of 2. So just go and put those slopes at each coordinate. And that's the makeup of the slope field. The biggest burden with the slope field is they would have like 8 different points, and you got to just find a derivative for all 8 different points. That's it. Down to 89 you guys can use. All right. So it's really the toughest part about slope fields is that they're tedious. There's just a lot of little simple algebra to figure out each slope. All right. For 0, for x. Well, yeah, x is 0, y is 0. X is 0, y is 1. X is 0. But the great thing about this is when x is 0, it's always going to give you a slope of 0. 0 times anything is 0. So that's why all these are slopes of 0 to the horizontal lines. Okay? So you see what I'm saying? It's not difficult. It's just you've got to be really organized. Because the math is quite simple. All right. If you know an initial condition, such as a coordinate, let's call it 1, comma, negative 2, then you can actually sketch the curve. All right? For example, this is our slope field for 2x. We don't know what our c value is, so we can't really show where the parabola is. But what we do know now is that there's an initial condition, this coordinate right here. So if I go to 1, up 2, or down 2, it goes through this point right here. That's a coordinate 1, negative 2. Which means, look at the slope here is this way, which means it goes up. But it tilts up a little bit more that way, and it probably goes a little further up. It comes down, it flattens out, comes up, and there you go. That's parabola. Right there. Well, because it's not curved. I really exaggerated it, just so you can see it. Okay? In this case, it's a parabola. I have this click to fade. Man, let's see if I have that here. No, I'm interested. It says click to fade. Did I have this in this? Oh, look, I did. There it is. Bam. There you go. Oh, I'm looking at this point right here. 2, 1. Looking right here. All right, so we can do a really, a couple of things with that, and it's really quite simple. Just get through it. That's the advice. So, what if we have to draw a slope field? Okay, I see out of all these dots here, I see 9 sets of dots here. I don't see any on the y-axis. We could find them out if we wanted to. Okay, here we go. X is -1 here, X is 0 here, 1 and 2. And for each one of those points, there are 3 y's. Aren't there? There's a y that's 0, a y that's 1, and a y that's 2. So this is how we do it. Ready? Don't everybody sound so excited at once. We have X, we have Y, and then we have our slope at that point. That's our slope, isn't it? Our dy dx. That's about 3x plus y. So, should we start with our -1s? And just go this way. So x is -1. There's -1 when y is 0, -1 when y is 1, and -1 when y is 2. Now let's just calculate 3x plus y for each one of those. It seems complicated. It's like making a table of points. And then watching the order. Okay, go ahead. What is it? The first one is -3, -2, and -1. All right? Now let's figure out when our x is 0. We have y is 0, y is 1, y is 2. But when x is 0, that wipes out with 3x altogether. So the answer is just going to be 0 plus 0, 0 plus 1, and 0 plus 2. So you see what I'm saying? Oh, it's not really that difficult. Every once in a while, I'll throw in a fraction, and you're like, yeah, you got to be careful. Okay, so it's what? 0, 1, and 2. Nothing crazy yet, is it? Not yet. So 1, 1, 1, 0, 1, and 2. Okay, if I take my x as 1 and I multiply it times 3, I'm always going to start with 3 plus whatever my y value is. 3 plus 0, 3. 3 plus 1 is 4. 3 plus 2 is 5. You'll see when we plot. You'll see when we plot the slope field. Yes. I didn't want to say it. I didn't want to say it. But look at the coordinates. Look at the slope, what's happening. -3, -2, -1, 0, 1, 2, 3, 4, 5. I mean, what do you think it's going to go the next 3? 6, 7, 8, maybe? I don't know. Let's see. When x is 2, we have 0, 1, and 2. Well, 3 times 2 is 6 plus 0, that's 6. 6 plus 1 is 7. 6 plus 2 is 8. All we're going to do is plot these for each coordinate. Let's start with our -1s. Okay? At the point -1, 0, which is right here, what's the slope? It's -3, which means it goes down kind of like that. What about at -1, 1? What's the slope? It's -2, so it's not quite as steep. Like that. And what about -1, 2? What's the slope? -1, so I don't know, kind of like that. See, so it kind of gets less and less steep as it goes up. Now we do the same thing for our 0 coordinates. And all we do is we put the lines there. Someone want to come up and put some lines up? Everybody at once looking at everything? Ava? Ava says Zach wants to? Zach. Yeah, drawing straight lines are difficult, children. I make it look easy in front of you. Yes, thank you. The 0 goes straight which way? Left, right, up, down? No. It is a straight line.
It goes up.
It goes this way?
Look for 0, 0, 0.
For this right here.
We go slow. That's right.
No, there's a slope, it's 0.
Yeah, that's what I'm saying.
It goes horizontal. No slope would be up and down, okay? So at the origin, it goes just like that. What about at 0, 1, which is right here? It's a positive 1. And what about at 0, 2? Positive 2, so it's a little steeper, right? And let's see. As you go. Thank you. See, you know, don't get enough credit. Yeah. Thank you. All right. What about 1 and 2 here? What do we got? Blues at 1, 0. What's the slope? 3. So it's going to be a little bit steeper than the one we just put. Like that. Then it's 4. It's a little bit steeper. 5. It's even a little bit steeper. See what we're doing? Right here, even a little bit steeper, it's 6, right? A little bit steeper, it's 7. A little bit steeper, it's 8. It does. It really, do you know what the worst part of this is? Having to write all these numbers down. Because it's going to be real easy when you're adding and multiplying to make a mistake when you're just going through it ones and zeros. It's going to be real easy to make a mistake.
But what if you write yourself as you?
Well, you just got to make it kind of obvious. Obviously, the slope of 4 is steeper than the slope of 1.
Yeah.
So don't make it the other way around. You know, then it's a big move. Okay. Not horrible. Not horrible. The worst part about that is making the table. That's the worst part about that. Oh my goodness. I should lower this here. Nothing in here? Oh my goodness, I got this off the line. And when I say off the line, I mean the internet. You thought it was who? No, it's not. It is not. Why would you? I wasn't. Terrible. Terrible. So to see or not to see? If we have an equation y equals x squared, right? We have an equation y equals x squared. There is the indefinite version and the definite version. Indefinite means we have bounds. Thank you. Because we just figured out that when there are no bounds, we did what in the beginning of class? We had to put a C because we don't know if there was a constant or not. We don't know if there's a constant. So, let's integrate this. What does that turn out to be?
Let's see.
Don't take the derivative of it. We're integrating it. Don't take the derivative of it. I add 1 and then I divide by that, right? So it's x cubed over 3 plus c. Because I don't know what that constant is. I'm now going to show you why we don't need a constant for the definite one. Do you really need to know the purpose behind whether we need the constant or no? Not really. You just need to know that if there are bounds, you do not put a C there. Okay? If there are no bounds, you put a C. So this is with the C. This is without my C. Huh. Now, beautiful. That beautiful Shakespearean. All right. So, what do I do with this one? I integrate it, and I get what? The same thing. That goes from 4 to 1, doesn't it? Here's the reason that we don't need this C. Okay? Here's the reason. If I were to integrate this without the bounds, I would have x cubed over 3 plus c, right? Which means I would have 4 cubed over 3 plus c minus 1 cubed over 3 plus c. You got it. What happens here? Well, this turns out to be 64 thirds plus c minus 1 third minus c. So what happens? The c's cancel. So this is going to end up being 63 over 3.
Oh, so you could put this here.
You could, but you don't need, it cancels out. So for future reference, I mean, now you know why. So whenever I ask you, you don't need to see when there are bounds. You don't need, and they call that definite because there are bounds. There's definitely bounding. This is indefinite because this works for everything. Okay?